Welcome to lecture number 6 for ECE 463 Modern Control, Lagrangian Formulation of System Dynamics. Now, in this course, we need to come up with a way to find the dynamics for nonlinear systems. That way we can simulate and control them. The tools that you learned back in circuits work very well for simple lump systems, such as RC circuits, RLC circuits. For more complicated systems, especially nonlinear ones, you need a better approach. One approach is the Lagrangian formulation of dynamics. What it does is it defines the energy in the system. Everything comes down to energy. If I know what the energy is and how the energy moves about the system, I know the dynamics. So with the Lagrangian, you've got a tool that can be used to define the dynamics of both linear and nonlinear systems. Now, before we start, let's go through a couple definitions. Kinetic energy is your 1/2 mv squared. Potential energy, PE, is mgh. As you raise a ball, it gets more potential energy, less kinetic energy. A del is a partial derivative. A d is a full derivative. And the two are different. If I want to take a full derivative contains partial derivatives. So like the full derivative with respect to t is what's the partial with respect to x times how fast x is changing, partial with respect to y with how fast y is changing, and so on. The Lagrangian is the kinetic energy minus potential energy. Now going back to partial derivatives. A full derivative includes partial derivatives. When you take a partial derivative, everything except the term you're considering is at a constant. For example, if I have the following function, the partial with respect to t is ignore x, ignore y, treat them as constants. I just get x squared y cubed, treat them as constants, times 4t squared. It doesn't matter that x is a function of t, y is a function of time. Those are taken into account in other terms in the full derivative, and I don't want to double count. So you can do a partial derivative, can anything that's not the term treat it as a constant. Likewise, full derivatives are different than partial derivatives, and we're going to be using that in just a sec. As an example, suppose I have x as a function of time, y as a function of time, and I've got my function f is 2 sine of x, y squared t cubed. Now find the full derivative of f with respect to t. Now to do that, I would use partials. It's what's the partial of f with respect to x times how fast x is changing, partial with respect to y times how fast y is changing, partial with respect to t, and how fast t is changing, del t is just 1. The partial with respect to x, everything that's not x is a constant. So treat the y squared, t cubed as constants. The partial of sine 2x with respect to x is 2 cosine 2x. Times how fast x is changing, x dot. And you can substitute x dot is just 4t if you wanted. Second term, partial with respect to y, everything that's not y is a constant. So sine of 2t is a constant, t cubed is a constant. Partial with respect to y is just 2y. And the partial with respect to t is 3t squared. Now one mistake that people oftentimes make is when you do the full derivative, I need this last term right here, partial with respect to x times the partial of x with respect to t. I need that x dot, but for this term I need a y dot. If you forget that, probably the units aren't right. This is df dt. I need something dt over here. And, well, you need that term. So going back to Lagrangians. The procedure to find the Lagrangian dynamics of a system is to first define the kinetic energy and potential energy of the system. Then form the Lagrangian. The Lagrangian is just the difference between the kinetic energy and potential energy. Then the generalized input will be the force on the mass is the full derivative with respect to t of the partial of L with respect to x dot minus the partial of L with respect to x. And this goes for every energy state. If x is the position, this will be the force on mass 1. If x is 2, force on mass 2, and so on. If x is a rotation, an angle, then this is actually torque. Now when you do this, you've got to pay attention to the full derivatives and partial derivatives. Again, they're different. So to start out, let's go through a simple example. Let's find the dynamics of a rocket. If I have a rocket launching into space, the potential energy is mgx, the height that goes up. The kinetic energy is 1/2 mv squared, or mx dot squared. So the Lagrangian then is just the difference. Kinetic energy minus potential energy, 1/2 mx dot squared minus mgx. Okay, so far so good. To find the force on the rocket, I take the full derivative of the partial Abel with respect to x dot minus the partial Abel with respect to x. The partial Abel with respect to x dot, get anything that's not an x dot is a constant. So m's a constant, g's a constant, x is a constant. I just get this term right here, mx dot. And this is 0 because there's no x dot. That's the partial with respect to x dot. The partial with respect to x is, there's no x's over here, there's an x, is just minus mg. Now take the full derivative. This is where you do the chain rule. The derivative of the second term is x double prime. Derivative of the first term is m dot. So if mass is changing, I actually get the force is mass times acceleration plus change in mass times velocity plus mass times gravity. And note that if the mass is changing, like you're burning fuel, the rocket's getting lighter, this term shows up. That's the neat thing about Lagrangian dynamics. You actually get this term. Other forms of dynamics don't really get this very easily. It is there. If you leave out that term, rocket's going to miss the target. So that's for a simple system. Let's do a more complicated system. Let's take a ball rolling in a parabolic bowl. I want to come up with the dynamics for this. Let's assume gravity's going down at 9.8 meters per second, and the shape of the bowl is 1/2 x squared. Again, this looks like a fairly innocent system, but it's actually fairly complicated. To start out, I need to define the potential energy and kinetic energy for the system. The potential energy is just mgy. Substituting is 1/2 mgx squared. The kinetic energy, this actually has two terms. I've got the translational energy of the ball as it rolls, plus I have the rotational energy as the ball spins. That'll be 1/2 mv squared plus 1/2 j theta dot squared, where j is the rotational inertia of the ball. The velocity is square root of x dot squared plus y dot squared. The rotational velocity is the distance it moves is r times theta, where theta is in radians. Take the derivative, the velocity is r theta dot. And note that y is 1/2 x squared, so y dot, this is taking the full derivative, is x dot. Partial with respect to x gives you x. Partial of x with respect to t is x dot. That gives the kinetic energy is 1/2 mv squared plus 1/2 j r dot squared. R dot is just v over r. Bringing the b's together, it's 1/2 m rotational inertia over r squared times v squared. Velocity is x dot squared plus y dot squared. Substituting for y dot, it's 1/2 m j over r squared x dot squared plus x dot squared. That's the kinetic energy. J is depending upon what type of ball you have. If I have a point mass, the rotational inertia is 0. If I have a solid sphere, it's 2/5 mr squared. Hollow sphere, 2/3 mr squared. Hollow cylinder, mr squared. I have to define what kind of ball it is. Let's assume it's a solid sphere, like a ball bearing. In that case, if I substitute for J, I can pull the masses outside. And the kinetic energy is 1/2 m plus 2/5 m gives you 0.7 m. Factor out the x dot squared. 1 plus x squared, x dot squared. And we're used to kinetic energy being 1/2 mv squared. The 1/2 ignores the rotational inertia of the ball. If you include it and it's a solid sphere, I get 0.7 mv squared. Okay, so now I've got the kinetic energy and potential energy. With that, I can form the Lagrangian. That's your kinetic energy, 0.7 m, 1 plus x squared, x dot squared, minus potential energy, 1/2 mgx squared. Now, the force on the ball, if you have a little person pushing on it, that force is the full derivative with respect to t of the partial Abel with respect to x dot, minus the partial Abel with respect to x. So going back to the Lagrangian, the partial Abel with respect to x dot is nothing, nothing, nothing. Here's an x dot. So it's going to give you 2x dot times this. Gives you 1.4 m 1 plus x squared x dot minus the partial with respect to x. So here's an x. Partial with respect to x gives you 2x times 0.7 m x dot squared. And here's an x. Gives you minus mgx. Now take the full derivative. And here's where we get the chain rule. The derivative of the first term will give you 2x x dot times everything else, 1.4 m x dot. Derivative of the second term is you 1.4 m 1 plus x squared x double prime. And the term over here. Now this term right here, notice it's 1.4 m x dot squared times 2, 1.4 m x dot squared. These cancel and leaves as a remainder 1.4 m x dot squared. This term comes down and there's mgx. So that's the dynamics of a ball rolling in a parabolic cylinder, a parabolic bowl. If I assume the force is 0 and the ball is just rolling freely, I just get the acceleration is 1.4 x dot squared g times x over 1.4 1 plus x squared. Nice nonlinear system. With that, I can now simulate it. What I would do to simulate it is, if I know x and x dot, I can calculate the acceleration. Integrate velocity, get position. Integrate the acceleration and get velocity. Time goes forward by dt. And I can just sit there and iterate, calculate where the ball is at any given instant. If I want to animate it, I need to show where the ball is. So just for fun, I want to draw the bowl. And I want to wind up with this display. This is a MATLAB animation of the ball rolling in a parabolic bowl. Drawing the bowl is pretty easy. That's just x goes from -2 to +2, y is 1fx squared, draw a line. For this little ball, I want to sit there and see where it is. And just for fun, it's kind of nice to draw a little line through the ball so you can sit there and watch it roll. To do that, I have to know how far the ball has traveled along this line. And the relationship between translation and rotation is distance is r times theta. So I need to know how long it's traveled along this line. If I then divide by r, I know how much it's rotated. And the rotation will sit there and let me draw that little line so you can see the ball rolling. Now to do that, I'll do the following trick. The length that's traveled along the bowl is r times theta. At any given instance, I know the velocity x squared, or x dot. I can calculate y dot. Again, y is 1/2 x squared, y dot is 2x x dot. So I know this term. I know x dot, so I'll then integrate 1 over r times the integral of 1 plus y dot squared times dx. So this is the program ball.m. I'm going to start out with x equals 1.5, calculate the dynamics. That's what I just did in using Lagrangian Dynamics. I'll integrate. If I know the velocity and no position, integrate to no acceleration, no velocity. That's every 10 milliseconds, 10 milliseconds later. If I know dx, I can calculate dy. dy is just x dot. The distance that's traveled is the square root of 1 plus y dot squared times dx. And then integrate the length that's traveled. To draw the ball, I will then draw a line through the ball. The angle that it's rotated is the distance that's traveled divided by the radius. I assume the radius is 0.05. Then draw a line through the ball. The current position, sines and cosines, to draw a line. I'll also draw the ball as a circle. So draw the parabola, draw the ball, draw a line through the ball, and here's what it looks like. Hit run. Start at 1.5. There's the ball rolling left. Goes fastest at the origin when I have less potential energy, more kinetic energy. And at this point I have all potential energy, no kinetic energy. Then it rolls back. So all that just to see a ball rolling in a parabolic bowl. Kind of fun to watch. So here's a question for you. It's rolling back and forth. What is the frequency of oscillation? Well, that's where you get into small signal models. If I linearize about zero, if x is small, x dot is small, then x dot squared x is really, really small. It's about 0. Again, if x is small, x squared is really small. Again, about 0. Take the nonlinear dynamics, ignore all the higher order terms, and I wind up with is x double prime is a constant, minus g over 1.4 times x. That means the frequency of oscillation is 2.646 radians per second. Or the period is 2 pi over omega. Period is 2.375 seconds. And if you simulate it, you'll see that's about what you're getting. The distance between the troughs, or the peaks, is 2.375 seconds. So, again, it's kind of an oscillator. Question for you. Is the frequency of oscillation constant? Meaning, would this make a good clock? In order for it to be constant, I need the acceleration to be constant times x. For example, if I have x double prime equals minus x, then the roots are plus minus j. X double prime equals minus 9x, then the roots are plus minus j3. So I need a constant times x. If I look at the dynamics, here's an x, that's good, but the rest of this is not a constant. So what that tells you is this is not a good clock. The frequency varies depending upon the amplitude. And you can see that if I make the initial condition 0.5 and run it. 2, 3, 4, 5, 6, 7, 8. It takes about 8 seconds to go. Again, this isn't running in real time. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12-ish. Takes longer. So the period depends upon amplitude. It's a lousy clock. Question then, what shape would give you a constant frequency? Well, it turns out somebody actually looked at that. The shape that gives you constant frequency is a catenoid. That's a hyperbolic cosine. If I could build a clock so that the pendulum would follow this shape, I would have a very accurate timepiece. No matter what amplitude the pendulum swing, I would have the same time. I actually had somebody try to build such a clock, but the mechanism to follow that path was so complicated that it actually made the clock less accurate than the standard clock, which just has a stiff arm and follows a circle. Clocks are really important. Back in the 1600s, 1700s, clocks, whoever had the best clock would rule the world, because to navigate, I can tell where I am north-south by looking at the North Star or the Southern Cross. East-west is really hard. If I had an accurate time clock, I would know that sunrise is at 6 a.m. in Greenwich time. If sunrise is later in the day, I know I'm further west. If sunrise is earlier, I know I'm further east. But I need an accurate clock. I need to know what time it is in Greenwich, England, for that to work. Otherwise, sunrise is at sunrise. So if you look at the old maps are very accurate north-south, but east and west, they're rather distorted. That's because, again, we didn't have good, solid, accurate clocks for quite a long time. If you go on some of the old ships, like in Boston or Baltimore Harbor, they've got the USS Constitution, and the captain's quarter is the chronograph, or it's a clock. The clock was all important. Only the captain could touch the clock. It was locked up under the captain's ward. Only the captain had a key to this clock. That clock is very, very important. It's one of the most important parts of the ship. That clock told you where you are, east and west. That was designed to keep time so you know what time it is in Greenwich, England. If I measure the time of sunrise, based upon the Greenwich time, I can tell you where I am. if this clock gets messed up, if somebody touches it and changes it, I have no idea where I am east-west. So again, that clock is very, very important. It was a major crime for anyone to touch that clock other than the captain. Again, clocks were cutting-edge technology in 1700. They got to be a major problem when Europe got connected by rails. It used to be that every city had its own time, and that's fine as long as people are just walking from town to town. Once you have trains going from town to town, then you really need an accurate clock. They need the two towns on both ends to be at the same time, because the tracks can only have one train on it at any given time. So if the two cities have different times, and one thinks the clock, it's 8 o'clock, and the other one thinks it's 10 till 8, if they both try to put a train on the tracks at the same time, you get major problems. So the most accurate clocks back then were the railroad captains. The railroad time is actually what led Europe to adopting a common time, basically because you needed to keep track of what time it was, what time the trains were going to be on the tracks, when they would get to the city, and everybody has to be on the same time for this to work. Today, we have the National Institute of Standards, where 1 second is defined as the duration of 9.1 billion cycles of radiation associated with the transition of a cesium atom. And it has a time clock that's used throughout the United States. And with that, everybody in the US knows precisely what time it is. Accurate to 1 part in 9 billion. But anyway, that's kind of a sidelight. So in summary, we've got the Lagrangian dynamics. What the Lagrangian dynamics do is if I can define the kinetic energy and potential energy of the system, I can tell you the dynamics of the system. And this works for both linear and nonlinear systems. You kind of see it's a little bit complicated, but it works. If I have a ball and beam system, or if I have a ball rolling in a parabolic bowl, the dynamics are fairly complicated. With the Lagrangian dynamics, I can get there. I don't know of any other method that'll get you this answer. So that's lecture number 6 for ECE 463, Modern Control, Lagrangian Dynamics.